This video is about exponential decay functions. Let's examine a question. DDT was a pesticide used in the earlier part of the 20th century to help with agricultural purposes. In 1962, Rachel Carson wrote a landmark book called Silent Spring that increased awareness about the exceptional harm it could cause to humans and animals. And by 1972, DDT's use was banned throughout the United States. Billions of tons were used before the ban, however, and the chemical has a half-life of around 15 years, which means it takes about 15 years for half of the substance to decay. Of each ton that was used during the first year of use in 1939, roughly how much remains today? How are we going to answer this question? We know that it's something we're looking for here is a half-life. And a half-life means it's the amount of time for half of the substance decay, for half the substance to decay. So every time that half-life is repeated, that amount of time, another half is gone. So we know that the function, a growth function like this, where we have ab to the t, can be used for these types of decay problems, because we know that b equals 1 plus r, where r is our rate of change. It also can equal 1 minus r, where r is our rate of change. And this is what we're going to be interested in, is a decay function, where we're looking at a times b to the t, where b is giving us our rate of change, and our change here is negative. When we're doing a decay problem, we know that it's going to look something like this, as opposed to a continuous growth problem, where we're looking at one that looks like this. If you're curious about the growth problems, there is a video about that in this series as well. But what we're interested in right now is decay. And we know that this follows this exponential type of function. What we need to do is figure out what this function is, and then how we can use it to figure out how much of the DDT, each ton of it, remains today. Just something to keep in mind. 1 ton equals 2,000 pounds. Alright, so we know in our problem that A is going to equal the initial amount we're interested in. B is going to equal that 1 minus r, where r is our rate of change, and t is going to be equal to our units of time. So our annual growth rate is what we call it here. And I'm sorry, not our annual growth rate, but our annual growth time frame, essentially. So is it years, is it weeks, is it months, what is it? In our case, t is going to be equal to 15-year periods. It's really, what is the growth period? And so in that case, a t equal to 1 is going to be 15 years. A t equal to 2 is going to be 30 years. Because what we're essentially saying is that every 15 years, we see half of the substance gone. So our r is therefore going to be equal to 0.5, which is 50%. So it's a 50% reduction. So A, the initial amount, times B, which is going to be 0.5, because 1 minus 0.5 is 0.5, to the t, and t is going to be in units of 15 years. Our A, our initial amount, we can do a couple of different ways. Let's start by doing it where A is equal to 1 ton. So we have 1 times 0.5 to the t. So when I want to determine how much is left, I'm going to have to figure out how many t's, how many units of 15 years. But before I do that, let's figure out what we're dealing with here along the spectrum of time. We said in 1939 that we had billions of tons that had probably been used throughout DDT's use, but in 1939 there were probably thousands of tons that were used. We're just interested in what's happened to each one of those tons. So what we're curious about is 15 years later, in 1954, how much of each one of these tons was left. So I want to do 1 times 0.5, 1. And that happens to be equal to 0.5. So I know that half a ton is left. And that makes sense, because what we're talking about here is for every 15 years, we see half of the substance gone. So 15 years later, in 1969, what are we going to see? We're going to see 1 times 0.5 to the 2. And then we're going to see that we have 0.25 tons, or 1/4 ton left. Because again, in these 15 years, we saw another half gone. So, how are we going to figure out now this time frame? Well, 2011 minus 1939 is equal to 72 years. 72 years is not divisible by 15. So let's move up to 75 years, which is going to be in 2014. So we're going to use 2014 to be close to right now. 75 years divided by 15 years is equal to 5 units of t. So what I want to calculate is 1 times 0.5 to the 5. And that is equal to 0.03125. So in 2014, we have 0.03125 tons left of every ton that was used. Let's see if we can draw this out. So we're essentially saying that at t is equal to 1 at the very beginning, so this is going to be 1939, we have 2,000 pounds, also equal to 1 ton. At one time period in, and I'm sorry, these numbers need to be like this. At 1954, which is one time period of 15 years in, we know that we have a half-life. So that's 1/2 of a ton, or 1,000 pounds, right here. In 1969, 2 units of 15 years in, we see that we have 1/4 of a ton, which is 500 pounds, or 1/4 ton. So that's going to be right here. We have 3, 4, and then 5. In 2014, we expect to see 0.03125 tons, which if I calculate that out, that's 2,000 times 0.03125, means that we have 62.5 pounds left. So 62.5 is going to be about right here. So we can see that our curve is going to look something like this as it goes down. So the answer to our question is there's 62.5 pounds left, or 0.03125 tons. But just to double check, let's see if we had done this where A was equal to 2,000 if we get the same results. Because remember, we could have done this in terms of units of pounds instead of units of tons. If that's the case, then our function would have looked like this. 2,000 times B, which again is 0.5 to the t. So let's try this for our particular time frame in 2014. 2,000 times 0.5 to the 5, and in fact that ends up equaling 62.5. So we know that we could have used this A either way and we would have been fine. So the answer to our question, how much remains today, is we can say in 2014, 62.5 pounds of every initial ton used in 1939 will still remain. I hope this has been a helpful video to help you understand how to use exponential functions that have to do with decay. Thank you for listening.